Right, cool. So that's the third topic. So before we did transformers, DC motors, so induction and synchronous generators slash motors are basically the next two. But the concept of it kind of overlaps a lot. So once you really understand the basics of one, the other one shouldn't be that big of a jump to catch it, right? It's basically just working on the concept of electromagnetic induction. Lenz's law, Faraday's law, and Lorentz law, which is the force part. And it's the same thing you're using over and over, right? So, well, I mean, you all should know this already, right? The basics of it. You have a three-phase AC supply, which means that the input is just three phases that are 120 degrees apart from each other. When you supply that to the stator, which is wound in such a way that the three phases will be 120 degrees apart spatially, it will basically create a rotated magnetic field. And when that rotating magnetic field cuts the rotor, so normally for an induction motor it will be a squirrel cage bar. They also have the wound rotor, but that one is the other exception, right? For most of the time it's a squirrel cage bar you'll be using in the exam. So when that rotated magnetic field cuts the rotor bars, it basically induces an EMF, and that EMF gives you a current, and when you have current flowing in a bar or a conductor, it will then produce its own magnetic field, and that magnetic field will basically chase the magnetic field of the stator. And well, once you have current in a conductor, it will produce a force. And then once you have the force, you basically have a rotation, right? Just admit. Let's see. Oh, one. Oh my god. Interesting. Alright, yeah, so that basically the process. Three-phase AC, rotate the magnetic field cut the bars, Faraday's law. When you cut the bars and you had the EMF give you a current giving you a magnetic field, and well, we know Lenz's law states that it will oppose, right? And then once you have current flowing in a conductor and it have the magnetic field, you'll experience a force. And when you have a force, you have torque, and in a rotation, it's the same thing over and over, right? So well, you know that the three phase is the input energy into the motor. Right, so that just basically going through exactly what I went through just now, just more in depth, so you can give it a read, right? In the exam, they could ask you to go through the process of how an induction motor works, right? So that's going through the parts that's important here. So the first part is something called the synchronous speed, right? So when you put in the three phases into the stator, that rotation, that rotated magnetic field, you call it synchronous speed, right? Because that's the speed at which the stator magnetic field from the source is rotating up. So you call it NS, and well, this P, you'll get to this P just now, but there's number of poles, so it will give you two things. It can give you the number of poles or the amount of pole pairs. So is it a PP or capital P? And well, F is the frequency of the supply. Most of the time it's 6 digits, but they will give it to any question. Right? And well, everything else that's summarizing the steps as to how rotation happens, and everything ends off with rotation. Yeah. So all this that's going through the steps. So there's the Lorentz law. When you have current in a conductor, it experiences a force. And which part is important here? This part here. So if you think about it, right, there's an important concept. Your rotor rotating at a speed which is the speed of the squirrel cage, which connected to your load, and then the stator rotating at synchronous speed. You need relative motion between, or relative difference between the speed of the rotor and the stator to induce a EMF, because everything is induced. To induce something, you need cutting. Always remember that. An induction motor works on induction, which is basically a magnetic field lines cutting a conductor. Yeah? So anytime your rotor, well, this will never happen, but theoretically, if your rotor speed is the exact same as your stator rotating magnetic field, the bars or the magnetic field will not cut the bars anymore. So if you have no cutting, you have no induced EMF, which means you have no current, and if you have no current, you have no torque, and if you have no torque, well, the motor itself, it won't immediately just drop to zero, but the speed will drop. And when the speed drops, the rotor now a bit slower than the synchronous speed, and the torque will start back. So if you actually listen to the motor, it will sound like it's pulsating. So it's speeding up, slowing down, speeding up, slowing down, speeding up, slowing down. So you will want that type of motion in your induction motor. Right? So just remember, anytime the question asks, can the rotor speed ever be the same as the synchronous speed? The answer to that is no, because you need a relative difference between the speed of the rotor and the stator. Because think about if you're chasing something, you can't chase something that literally alongside you, which running at the same speed, and you can't chase something that behind you. You can only chase something that's in front of you. Right? So that relative difference in the speed is what giving you the cutting and literally everything else leading after that. Right? So the slip basically ensures continuous torque production. So you'll get into what slip is, but the idea is you need a relative difference between the stator rotating magnetic field and the induced rotor magnetic field. So this kind of summarizes what I went through just now. So three-phase rotator summarizing everything, right? So this part here, NR, if NR ever reaches NS, went through the same thing, right? The rotor will slow down slightly, as the pulsating I was talking about, right? After it slow down, the relative difference will return. EMF will induce again, the current will flow, torque will be produced, and everything will come back to normal. But it will kind of pulsate. The way it's a pulsate, you want it to be a continuous motion, right? So that's important. The induction motor can never ever run at synchronous speed, right? Cool. So rotor types, I mean, slight idea for this slide is you have two types of rotors. You have the squirrel cage, which you all know or accustomed to, and you have the wound rotor, right? So in an exam, you could just ask you to go through the advantages and disadvantages of these two types. So honestly, go through these, memorize like 3 or 4 in each, but the main differences in them are these two. So high starting currents, low starting currents, excellent starting torque, low starting torque. So these two are the main differences in terms of application, right? The speed itself is variable when you wound router. That's a good one. But everything else, this one just easier to maintain and it's cheaper. This one it gives you more application in terms of use, but more expensive and higher to maintain. So it depends on your application, right? So aka know the difference between the squirrel cage and the wound router types. This one is the most popular one and what you will see in the exam. Okay, cool. So we kind of touched on it before. So the synchronous speed is the speed at which your stator magnetic field rotating at. So in this picture, you have purple, orange, and green, right? So you basically have inputs, inputs, inputs. So you have here, well, I kind of labeled it wrong, but you have here B phase here, C and A. Each of these phases is 120 degrees apart from each other spatially. So when you connect this into the stator, when the current flows through the coils, it will basically give you something that looks like a rotating magnetic field, right? I'm just admit somebody, not sure who. Yeah, they give him more work to do to edit. Cool. Right. Yeah. So three-phase input, rotating magnetic field in the stator. How does it look? It just looks like alternating north and south. That's true. Kind of just rotating. It's not physically rotating. It's just a magnetic field rotating. So you call this omega S or Fs, right? So once that magnetic field cuts the rotor bars, this will then generate its own little magnetic field and it will just try to chase. So the north will try to chase the south and the south will try to chase the north. But it will never catch it. It can't catch it. If it catch it, it have nothing to chase anymore. It's all a chase. If you get what you want, you have nothing to chase when it gets what you want, right? So you'll need a little difference between the speeds to keep the rotor bars being cut by the magnetic field of the stator to keep all the induction happening, right? So yeah, so basically the synchronous speed is due to the number of poles and the frequency, which is from the equation, right? So P is the number of poles per phase, and well, PP is the number of pole pairs, right? And what F is the frequency. So you have two equations. First one, I mean, if they give you pole pairs and they need poles, well, you just divide the poles by 2 and you get the pole pairs. Yeah, that's important. But most of the time, they'll either give you the number of poles or the pole pairs. So you're either using this one here. So if they give you a number of poles, it's 120 F on P. And if they give you the pole pairs, it'll just be 60 by F on P. Pole pairs. Let's know the difference. Have a different equation for NS based on the number of poles or the number of pole pairs, whichever one they give you. Keep that in mind. Right, so this there to just derive it in terms of angular speed, but you don't really need to do this, but if they give you the speed for some reason and you need to convert to omega s, you'll be just using this. Right, but if you want to keep it in omega s, if they give you the synchronous speed in terms of omega, in terms of instead of frequency, instead of converting, you can just keep it there. So the two forms is basically this one here. So I'm gonna write it out in a neater way. So this was in terms of poles. So if they give you the angular frequency instead of the frequency, you can still convert it to synchronous angular speed. And same thing down here. If they give you the number of pole pairs, that'll be freak on P. Same concept. Just in terms of angular frequency instead of just frequency, which is F. Yeah. So two important equations, but I mean, if you can't remember it, just convert the omega to n and just use n, because most of the time you have to use n for everything anyway. So if you're not comfortable with it, just convert the omega to n. Yeah. Either way, you get the same answer. Okay, cool. Right, slip. So what slip is, we know, is the difference between the rotor speed and the synchronous speed. We need that difference, right? So they basically made an equation to represent that relative difference, right? So the equation is basically a synchronous speed subtract a rotor speed divided by a synchronous speed. That is what slip is. So it's synchronous minus rotor and synchronous. And same thing in terms of angular frequency. You get the same answer. Okay, cool. Nice. So from induction, probably the most important thing that you'll have to know how to draw is the equivalent circuit. So from transformers, the start of it is basically the same thing. It literally looks like a transformer. This is a derived equivalent circuit, but the actual equivalent circuit to have something like this, right? It's technically a transformer. It's just you're not tapping the current induced in the rotor bars to go to the load. Yeah, literally just using that current in the bars to generate a magnetic field in the bars to continue rotation, right? You don't need to know this one, I just put it so you all can see it. So initially you have an input into the stator, and just like a transformer, you have your core losses, you have your I1, so you have your stator copper losses, and you have a stator flux leakage. That's like transformers. And you have your E1, then you have a space between, or air gap, between your stator and your rotor. It's not just like a transformer, it's not physically connected to each other. So the flux that is generated in the stator, it cuts the rotor, and when it cuts, it generates a EMF, just like a transformer, and that will give you a current, just like a transformer. And that current also passes through leakage, so also have leakage losses, and then the copper losses, which is a bit different from transformers. Your copper losses is based on your value of slip. Yeah, it determines by value of slip, right? So that's the only difference from the transformer to the induction motor. So all they did, instead of using two separate circuits to model it, they just basically went from here into just one nice circuit that grouping everything together. So now in this circuit, well, this measuring the physical space between the stator and the rotor. So that is a PAG. And well, they referred these values onto the stator side. Remember, it's not primary and secondary, stator and rotor. So they refer the rotor losses onto the stator side. So you have GXR prime, RR prime, and then this piece here, it basically just modeling the load resistance. So however the load have this is modeled by, because as the load changes, the speed will change. And if the speed changes, the slip will change. And if your slip change, your losses will change. That's how they link together. Because think about it, if you're on a motor and you put more weight on it, you expect it to slow down. And if it slow down, the relative difference between the rotor and the synchronous speed will increase. Yeah, which means the slip will change. And if the slip change, you can look back in the equation and see where the values will change, right? But the importance of this equation is now, instead of having two currents, you just have one equation, I1. So I1 basically passes through RS, GXS, GXR prime, and RR prime. It passes through the entire, all of them in series with each other now, which makes calculations a lot easier to do, right? And one more thing, you'll probably see that I have two resistors here. So what they did in the equivalent circuit, they just combine these two, and it just end up with this here. So if you're doing any calculations, you don't need to do these two separately. You can just, the combination of them is basically just RR prime on us. Yeah. So if you want I1, you could just use the same equation, V is equal to IR. In this case, R is our impedance, so you have your R's and your X's, and you basically have your voltage. So with the voltage now, you have two things you have to keep in mind, right? We'll get to the just now. The configuration the induction motor connected in, that's important, and the value of the voltage, because sometimes some people just forget that in a delta the line and the phase is the same value, but in a star your line voltage and a phase voltage is different. This is a per phase equivalent circuit, which means if they give you a line voltage you have to convert it to phase, but you have to know the configuration, because some configurations, aka delta, is the same value, but in a star you have to do the root 3 relationship. So just keep that in mind. Okay, well, I mean, this one you can read it through. That's going through the relative difference, right? So, the big part, just summarizing. All this is basically a proof. 'Cause I think Kelsey had asked me something about it. This whole slide here is literally just proofs. That's going through how they went from the two circuits to just one. So, just going through it. There's a relative difference in speed, which we know, which is ns minus nm. Right? And well, we know that difference in speed is directly proportional to the induced EMF in the rotor. Yeah, so the larger the difference is in speed, is the more cutting you're gonna have, which means that the induced EMF gonna increase. Because remember, if you moving slower than anything you're chasing, you could literally see it better because it's further in front of you. But if it's just real close, it'll be a problem. Yeah, so the bigger the difference in speed is the more cutting you're gonna get. Yeah, the closer you reach to it, you'd rather run that fast because it's right there, right? So that's what this telling you. So at standstill, which means that the rotor not moving, yeah, difference in speed is the same thing as your synchronous speed, which means that it's not moving, right? Remember the cutting would be at high. All this deriving here is this here. All this whole thing here is just a proof to show you how you went from two circuits to one, right? So this is just telling you that the induced EMF in the rotor is equal to the E2 voltage multiplied by the slip. Because remember, everything is due to the relative difference between the rotor and the stator speed. Everything is due to that, right? And well, on this side, we've the difference between the FR and FS. So same thing, well, we know the speed, the relative difference in the speed is directly proportional to the rotor frequency. And same thing with this. So they literally just did the derivation and end up with this, which is the same thing as before. So they're telling you that, which makes sense. Your rotor frequency is equal to the slip or a portion of your stator frequency because they never rotate at the same speed. So your rotor speed will always be a subdivision of your stator speed in terms of frequency. Yeah, and we'll add this one here. At standstill, slip is equal to 1. Why at standstill slip is equal to 1? Because slip is ns minus nr on ns. If at standstill this is 0, ns and ns is 1. Yeah, so at standstill slip is equal to 1, right? Which is why on top here, this drop off also. At standstill, nothing moving, right? So if at standstill, nothing moving, you're going to get the maximum amount of cutting because you're not moving, right? And well, this kind of generalizing and summarizing everything. So there's more of a proof, right? Not really something you will ask in a question. It's good to know it though, especially this one, because if you have the slip and the stator frequency, you could get what frequency the rotor rotating at. Yeah, this one less popular, but this one more popular. Yeah. Right, cool. So there's the backbone and everything. So something called the power flow for the induction motor. The better you understand this power flow, is the easier the question can become to you. Because majority of the questions is just in bringing certain points, so you starting from certain points, and you're asking you to go like different places, all over the place. So it starts off with your input power, which is Pn, right? So we know Pn, root 3, V line, I line, cos theta. That equation will never change. Remember, your input power going in, but the voltage you use V line. But in the equivalent circuit, you use in phase. That's when you draw in the equivalent circuit. But the input power into the system is just root 3 V line, I line, cos theta. Yeah. So you have your input power. After the input power, you basically have your losses in the stator. So you have your copper losses and your core losses, just like a transformer. And then you keep going. After these two losses, you have the power that the air gap will see. Yeah, so you call that the rotor power. So that is the useful power that the rotor going to use. And then from that power now, you basically have your rotor losses, which is copper losses. Remember, everything here is real losses, right? We have no X or reactive losses here. And after that one loss on the copper side, you basically end up with your mechanical power, which is the power that literally going to be used to do useful work in your system, right? And from that PMEC, now you have to subtract your frictional windage. Remember, this is a three-phase value. So, and this PMEC will be a single phase value. So one thing a lot of students just forget to do, when they're trying to get efficiency, output power, and all these things, they forget to multiply the mechanical power by 3. Because this is everything here is per phase. Everything is per phase. From the time you go output power, is when you had to start to remember that, oh, it's 3 phase power. So you have to multiply the 3 PMAC by 3 when you go into this portion. So from here, just know that is 3 phase system. Everything from before is basically per phase. But you could scale this up, like just multiplying everything by 3. But most of the time, everything's single phase up to here. And then from here, you have to think about the 3 phase system, okay, going up to the output of the motor. But anyway, so after the PMEC, you subtract your frictional windage losses, and after you subtract that, that'll be the actual output power that actually gonna be used to move the shaft, which you call it peanuts. Yeah, and this peanuts, and you have the input power. These two things will basically come together to give you efficiency. So in this case, P out, you just call it peanuts, and P in. Yeah, and same concept. This efficiency will never change. Right? The equation is the same thing. Output over inputs. We have different ways for P out and P in. We went through that in transformers. We went through it in DC motors. and you're gonna keep doing it over and over. It's the real losses that you're always using. Yeah, and you always have P out and P in for each other. Yeah, right, some equations now. So we're going to do just now. We know what P in is. So after P in, you have your stator losses. So you have your copper losses, which is I1 squared RS, and you have your core losses, which is IU squared R, similar to transformer, same concept. After those two losses, you have your air gap power. So whatever left after you subtract these two is your air gap power. And the equation for air gap power is well, PAG, which is I1 squared RR prime on S. These are important equations to remember. Yeah? Even if you forget it, just know P as I squared R. And everything in series. And the current is the same thing. Yeah? So just know for PAG is RR prime on S. I'll show you how you can see this in the circuit. Then from that power now, yeah, somebody say
Just to
something.
make sure
Yep,
you're recording this, right?
yeah,
Okay, cool.
yeah, so cool. So after this power now, some of it will go to your root here, root of copper losses. A nice equation for the root of copper losses is S by PAG. Yeah, or just I1 squared R. Same concept. Then you have your Pmec. So the equation for Pmec is PAG by 1 minus S. Then you just keep going. So now when you output power now, you have to multiply the Pmec by 3 because it's output and then subtract the frictional windage. This value is a three-phase value. When they give it to you, they won't give you a per-phase frictional windage because the frictional windage is for the entire motor. Yeah, yeah. And then well, the shaft power, you're gonna use that shaft power to get the torque. And the torque will just be a P net divided by your angular speed. Yeah, so it'll be P on omega R, which is similar to DC motors. Yeah, and that's called the power flow. So to know this, take a piece of paper, start from your PN and go through all the equations straight back. So from the equivalent circuits itself, I'm gonna go back to the good equivalent circuits. So that's basically what it's telling you here. So your input power, then you have this loss here, then you have this loss here. You don't see this because that's a reactive component. And then whatever power is left after the RS is basically what here you're going to see. And you don't see this in the circuit. So the next loss that you will encounter is this loss, which is just R prime on S. Yeah. So from the circuit, you kind of see the equations, but if you don't, to beat up. But make sure you know your equations as imperative to the calculations of the question. Yeah, right, next. Important thing is the I1 current calculation. You're basically just using V is equal to IR. But instead of R now you have Z. Because you have real and reactive components. So I1 is equal to V phase divided by, so you have the R, so you have two sets of R's. You have this one here, and you have this RR prime on S. That's actually the full circuit here without the piece here. So you need to calculate the slip first before you calculate I1, right? And well, then you just be J XS plus XR prime. When you do this, you will end up with the power factor for the current and everything, because you'll get the angle. Yeah? So if you ever see a question asking you for the power factor, you can literally just get it from the angle of the current. Because that's what power factor is, the angle between the voltage and the current. Because voltage most of the time is at reference. Yeah, so important equation. And also this is the full equivalent circuit. Cool, so torque equation. So these type of questions, I think I did a question similar to this with you all. So it's the same concept, right? He will ask you about starting torque, max torque, and all them stuff. So the torque equation is basically this. You pull out all the constants and you end up with K. Right? And then this is the final equation in terms of K, S, and alpha. K, well, you know K is your constant. Alpha is your X and R ratio, which is RR prime and XR. And what S is your slope. Right? So let's have a graph for your torque. So this is basically torque speed graph that they talk about. So you have your pull-out torque, which is your max torque. This kind of unstable starting torque, and it's the same graph. So it basically ends n is equal to ns, which slip is 0, and then at startup n is 0 and the slip will be 1. Yeah? So when the slip is 1, you basically can get a starting torque, and somewhere in the middle here, when s is equal to alpha, some value of alpha, you'll get your max torque. Cool. But anyway, so the starting torque is when s is equal to 1. So all you're going to do is, in the equation itself, you will calculate the value of k because you'll have all these parameters. You will calculate the value of alpha because you'll have these parameters. And to get the starting torque, you basically just make s equal to 1 and you basically just solve for torque. That is all it is. Just to remember, the starting torque occurs when s is equal to 1. You will have k and you will have alpha. Sometimes they actually give you the value for both of them one time. Right, so that's the motor will develop max torque when this, okay. For max torque now, that value of max torque will occur when the slip is equal to the rotor resistance or the XNR ratio of the induction motor. Yeah. So when slip is equal to alpha, that's when your max torque will occur. So all you're really gonna do is you're just taking the value for alpha and you're making the slip. And you literally just solve for torque. It's the same thing over and over. You just have to remember how they got it. So max torque occurs, or starting torque is when s is equal to 1, and max torque is when s is equal to the value of alpha. And you have alpha already. So if I was to sketch this graph, the 2 points you're looking for is this value here. You're looking for the shape, you're looking for your putting your max torque at the value of alpha, and looking for you to bring it back down when ns is equal to n. So this is important when you're drawing it. I will obviously label the axis as a speed torque or a torque speed technically graph. Yeah, so that is basically starting torque and max torque. With magnetization branch, I mean, you all should know this from transformers, right? It's the same concept. They will give you your no load current, or they could ask you to get a no load current. Number this I1. So I in the same thing, I1 plus I no load. Most of the time they give you I no load, so they'll say I no load is like 2 minus 4G. And you're just kind of just using that to get RO and XM. It's the same concept, right? So you will have V and you'll have IO because this is V phase. The cos theta part, same thing, is literally the same thing as transformers in terms of the open circuit test. You calculate your cos phi, and once you have your cos phi, that's using that angle to get RO and XM. Same concept, it literally never changes. It for induction, synchronous, transformers is basically a open and a short circuit test, just give it a different name. But it's basically the same steps in terms of the operation of it. Right, next one is efficiency. Same thing, it have two equations for efficiency, but most of the time you'll know what peanut is. So remember, you have two ways you can look at the efficiency. You can look at it from the PN point of view, or you can look at it at the output point of view. It have two equations for that. At any note, so you could check it and see. But most of the time, peanut is the easiest one to use. Yeah, and well, just like before, we have this here, which is your output, which is peanuts minus your frictional windage, and notice everything you multiply by 3 because you have to scale it up. All the CU and all them things, those were per phase values. So when you're doing your efficiency, to get your output power, your losses you have to multiply by 3 because your copper losses and your nodal losses is for one phase. You have 3 other phases. Alright? So just keep that in mind. So I think this one is P out, or well, peanuts, and this is your peanut here, and this here is your losses. Notice you're not multiplying the frictional windage by 3 because that is already a 3-phase value. The only thing you have to multiply by 3 is the copper loss and the no load losses because those were per phase. Yeah, and well, I mean, this one kind of explanatory, right? The efficiency connects the mechanical output power to the electrical input power. That's the base way it is. I mean, I kind of redundant, but that is how it functions. Okay, cool. So no load test, we literally just mentioned it just now. Same concept. But if they give you a no load test question, you just have to know they're going to give you a P, V, and I. You're using those three to get cost phi, and then you end up with RO and XM. Yeah? This giving you an angle. Once you have that angle, IO and IM, you just resolving it into its horizontal and vertical components. Yeah, the same concept, same thing as transformers. But just note that in order to get a no load speed, your slip basically had to be zero, right? Because it's not supposed to be moving, right? So when that happens, that whole branch with RR prime on S if S is zero, there's gonna be infinity. And infinity is synonymous to open circuit, which is why it's just an open circuit. That's why it does obtain an open circuit in an induction motor. Yeah. Cool. The next one, short circuit, locked rotor. So same concept, right? So this is what does give you your REQ and your XEQ, and it's the same concept as before. So you have P, they'll give you P, V, and I, you calculate the angle. And the best way to do this once you have the angle is just to use the impedance triangle. So you have the angle already. So if you want the real part, it will just be ZQ cos the angle. And then if you want the X, it will just be ZQ sine the angle. This is the one that is used over and over. Because this will give you the angle. Let's do cos inverse of that, and you have the angle. So it's like a normal triangle. So if it was 40 degrees, you have Z, and you have R, and you have X. Yeah. So let's keep that in mind when you're doing the questions. And well, the next one is the stator resistance test. The things you have to remember for this one is if it's a Y connection, they will give you R. If this is Y, the R1 will basically just be half of the measured resistance. So you're taking a, I think you already did this in lab. You're taking an ohmmeter and you're measuring across two terminals. And if it's a Y, the resistance will just be half. And if it's a delta, it will just be 3 and 2 of that measured value. Yeah, that's basically what the stator resistance test is. You're basically trying to measure the stator resistance to check for degradation. Don't know if it's weighing out and cool. Well, this kind of just summarizing some stuff, but I mean, know what configuration you want to in. Always use phase voltage, whether it's delta or star. This one is the efficiency, and you know the power factor and the input power related. So two equations are very important. And I think that's really the end. So, well, we have this one. But this just summarizing exactly what I did. Just pay attention to these things here. The common mistake people make is forgetting to convert percentage for efficiency, because is a actual efficiency is measured in a percentage, right? Ignore any power factor, any input power. Real people will just think is root 3 VI. Just forget the cos theta part. And the most important and the biggest mistake is mixing line and phase values. And the other biggest one is the single phase formula instead of the three phase formula. When you're doing efficiency, you have to remember that is a three phase device and not just one phase. Cool. Right, so any questions on anything I went through there?